Hey there, and welcome. Have you ever wondered if you could use something as common as electricity to literally break a chemical compound apart? Well, you absolutely can, and the process is called electrolysis. It's an incredible technique that uses electrical energy to create real, tangible chemical change. So let's dive in and see how it all works. Here's our game plan for this explainer. We're going to start with the spark, getting to the heart of what electrolysis actually is. Then we'll meet the players, the essential cast of characters that make it all happen. After that, it's time for the main event, where we see the process in action. And finally, we'll check out the payoff, some of the amazing ways we use this in the real world. All right, let's kick things off at the very beginning. To really get a grip on what's going on, we need to understand the fundamental idea behind this powerful process. What's the core principle that makes it all possible? This is really the big question, isn't it? We use electricity to power our phones and light our homes, but can we actually use it as a tool, a sort of chemical crowbar, to pry compounds apart piece by piece? The answer is a huge, definitive yes. The name itself gives us the biggest clue. Electro obviously refers to electricity, right? More specifically, the flow of electrons. And lysis, that's a Greek word that means separating or breaking down. So put them together and you get electrolysis, which literally means separating with electricity. It's basically a chemical decomposition that we force to happen by passing a current through a special kind of liquid. Now, this is a really important distinction to make. When electricity flows through a copper wire, it's a physical process. Electrons are just zipping along the metal. But with electrolysis, it's totally different. The current is carried by ions, charged particles that are physically moving through a liquid. And because things are moving and reacting, it's a chemical process, meaning a real, permanent transformation is happening. Okay, so to make electrolysis happen, we need a specific set of components. Think of it like a stage play with a cast of characters, where each one has a super important role. So let's meet them. First up, we have the electrolyte. This is basically our stage, the medium where all the action happens. It's a substance, maybe a salt or an acid, that breaks apart into those free-moving charged particles, the ions, when it's melted or dissolved in water. Without these guys floating around, the whole show is a no-go. Next, let's introduce the anode. This is the electrode that's hooked up to the positive terminal of our battery or power source. And because it's positive, its main job is to attract the negatively charged ions. The anode is where oxidation occurs, which is just a fancy way of saying it's where things lose electrons. You can think of the positive anode as being electron-hungry. It just loves to pull electrons away from anything that gets close. And on the flip side, we have the cathode. This one's connected to the negative terminal, so it's loaded with extra electrons. It attracts the positively charged ions and is the site of reduction, which, you guessed it, means the gaining of electrons. The anode and the cathode are our two lead actors. Now for our supporting cast. Meet the cations. These are the ions with a positive charge. And where do you think these positive guys are headed? Yep, opposites attract. They're drawn straight toward that negative cathode. It's an easy one to remember. Cations are attracted to the cathode. And finally, we have the anions. These are the negatively charged ions, and, following that same rule of opposites attract, they make their way over to the positive anode. See the pattern? Anions head to the anode. And this table just pulls it all together beautifully. The positive anode attracts the negative anions, and that's where they lose electrons or get oxidized. At the same time, the negative cathode attracts the positive cations, where they gain electrons or get reduced. It's like a perfectly choreographed chemical dance. Seriously, this chart is the key to understanding the whole thing. So, we've met the whole cast. We know who they are and what they do. Now it's showtime. Let's see what actually happens when we put all these players together and flip the switch. Let's walk through a classic example, the electrolysis of molten lead bromide. Here's a look at our setup. We've got our power source, like a battery. We have two graphite electrodes, which will be our anode and cathode. And they're dipped into this crucible, which is holding the lead bromide, that we've heated up until it melts into a liquid electrolyte. So here's how it all unfolds step by step. First, when we melt that solid lead bromide, its ions break apart and can finally move around freely. We've got positive lead cations and negative bromide anions. As soon as we turn the power on, the migration begins. The positive lead cations head for the negative cathode, and the negative bromide anions start swimming towards the positive anode. Then, the real magic happens right at the electrodes. So let's look at the cathode first. When a positive lead ion arrives, it finds a place that's rich with electrons. Each lead ion grabs two of them. This process, reduction, neutralizes the ion's charge, turning it back into a regular old lead atom. As this happens over and over, a layer of molten lead metal actually builds up right on the cathode. Meanwhile, at the electron-hungry anode, the exact opposite is going on. Each negative bromide ion arrives and gives up its extra electron. That's oxidation. These newly neutral bromine atoms then find a buddy and pair up to form bromine gas, which you'd see bubbling away at the anode. And just like that, we've used electricity to neatly split lead bromide into its pure elements, lead metal and bromine gas. Pretty cool. Now, this is way more than just a neat lab experiment. This process is actually the backbone of some huge industrial technologies that we all rely on every single day. Let's see how this basic principle leads to some major real-world breakthroughs. One of the most common applications you've probably seen is electroplating. Using electrolysis, we can deposit a super thin, durable layer of one metal onto another. In this kind of setup, the object you want to plate, say a brass spoon, is made into the cathode, and a piece of the metal you want to plate with, like pure silver, becomes the anode. It's used everywhere, from jewelry to shiny car parts. So why do we bother doing this? Well, there are two huge reasons. First, for decoration. We can take a pretty inexpensive base metal and give it a beautiful, shining layer of silver or gold. But maybe even more importantly, we do it for protection. That layer of nickel on a wrench or chromium on a car bumper is there to prevent it from rusting and corroding, making it stronger and helping it last way, way longer. Here's another massive one, electrorefining. This is how we get the ultra-pure metals that are absolutely essential for our modern technology. For example, to purify copper for electronics, you make a big, impure slab the anode and a thin sheet of pure copper the cathode. When you turn on the power, only the pure copper ions travel across and plate onto the pure sheet, leaving all the junk and impurities behind. This process is vital for the materials in your smartphone, your computer, even in solar panels. So there you have it. We've seen how electrolysis uses electricity to precisely break chemicals apart, which lets us plate, protect, and purify all sorts of materials. This simple principle of splitting with electricity has literally built entire industries. It really makes you wonder, now that we have this incredible tool to deconstruct matter, what new things can we build with the pieces?